Vision of all. So, very good morning to all of you present here. A bright sunny morning today in Shillong. First of all, I feel very privileged and honored that among us, Professor T. Srinivas sir from Indian School of Sciences, Bangalore, from the Department of Electrical and Communication Engineering is among us. We feel very happy and glad. And Professor Aljay Singh, Dean, School of Technology, Head of the Department, Dr. Rupapan Subedar sir, Dr. Sushanta Pamidatta, my colleague, Pida Madam, and Dr. Juesh Binong, dear research scholars, and today's presenter, research scholar, Ms. Balbindar Kaur. I would like to welcome as well as thank for being here to pay attention to appreciate the work of Balbindar, what she has done in last 5 years, and on as well as I would like to thank Dr. Professor Srinivas sir, who has happily agreed when I visited IIS Bangalore in 2019 to get his consent to be an external examiner. So we feel very happy and being sir is from IIS Bangalore, as you know, number one, premier institution in India. India is known because of this IIS Bangalore as far as research and academic contributions are concerned. So we feel very, very happy, sir, being in Northeast. And thank you so much for your kind support, help. So with your kind permission, I would like to invite Ms. Balbindar Kaur to present her final Ph.D. Viva Voce seminar. Sir,
thank you also. I'm very happy to associate with your university.
Yeah, thank you, sir. If situation will prevail normal, we will be very happy to invite you in our department, in our university. So, yeah, yes, sir. So with this, Balbindar, please share your screen and go ahead.
Yes, sir.
With your presentation.
Yes, sir.
And best of luck.
Thank you, sir. Okay. So, sir, the slide is visible?
Yeah, slide is visible.
Yes, sir. So, sir, I can start.
Just hold on. Let me take first a snap. Snap of first piece. Okay. Thank you. Yeah, go ahead.
Okay, sir. Thank you, sir. Good morning to you all. My name is Balbindar Kaur. Today I am going to give my Ph.D. Viva Voce seminar on modeling and designing of space-division multiplexing based multi-core Erbium-Doped fiber amplifier under the supervision of Dr. Subhash Arya, Associate Professor in the AC Department of SOT NEHU. So these are the outlines of today's presentation: introduction, motivation, background study, problem formulations, objectives and methodologies, mathematical modeling divided into two sections, one for to model C-band multi-core EDFA, another to model the mode of light traveling through multi-core fiber. Then the contributory chapter, the thesis. So there are three contributory chapters. I'll discuss the results and discussions and summary of each chapters elaborately, then come to the conclusions of the overall thesis work, limitations and future scope of the present work, publication out of the thesis work, references, acknowledgement. So introduction. So the main significance of optical fiber is that in this scenario and in future also, the whole wall is connected with a knitted communication network via optical fiber, because the information that is can be transferred to any part of the wall from another part of the wall with high bandwidth, low loss, and high speed. Some of the examples are like a newspaper, a movie, or a TV program that can be easily available to the whole wall at the same time, which is possible through optical fiber. Then also the second example, let us take a design team that want to communicate its design to the manufacturing team without any delay, which can be possible through optical fiber. Then a video call between a multiple locations can also be done through a optical fiber. So you can see that the whole wall is connected with an via an optical fiber network. So my main research aim is to support increasingly information-driven society and economy. Then the next goal is to boost the weak signal, that means to amplify the weak signal for long-haul communications. Then the third goal is to minimize the crosstalk with high-speed transmissions. And to obtain the above goal, the recent research are going in optical fiber to convert the single-core optical fiber into a multi-core fiber. So this is the picture of a single core which is converted into a multi-core fiber where multiple numbers of core are incorporated inside the cladding, single cladding. Then to achieve that, the multiplexing technique is one of the solution, which is the space division multiplexing technique. And along with space division multiplexing technique, erbium-doped fiber amplifier is used for in order to amplify the weak signal for long-haul communication. So there are different multiplexing techniques like TDM, and mostly used by the researcher are TDM, WDM, and space division multiplexing technique. In the right-hand side, you can see the graph where the y-axis is showing the system capacity per fiber along with the year. So until 1980, TDM was used by the researcher for electrical multiplexing. Then in 1990, WDM came into the scenario for capacity enhancement, and the WDM along with optical amplifier, that is erbium-doped amplifier, was a breakthrough in that year 1990. Then around 2000, digital coherence scheme was used by the researcher to increase the spectral efficiency with different modulation format. Then from this graph you can see that around around 2000 to 2010, a limit has reached for single mode fiber. So 100 terabit in research and 10 terabit is used in commercial. So in order to overcome that limit, that 100 terabit limit, this space division came into the scenario. So this space division multiplexing improves the capacity with cost per bit fiber. So what is this space division multiplexing technique? It is a method through which a transmission media physically separated by a waveguides or a space so that there will be a less interference. The spacing should be that much suitable that there will be no interference. And that space division, there are two basic strategies to achieve spatial separation within fiber. One is the few mode fiber and another is the multi-core fiber. So below these are the figure of multi-core fiber, multi-mode fiber, and the multi-core multi-mode fiber based on space division. The parameters that are used to design these fibers are the core pitch, core diameter, cladding diameter, and the outer core cladding distance. And the major parameters from this designed fiber based on space division are crosstalk, gain, noise figure. Then amplifier, the erbium-doped amplifier. So first in the year 1987, Dr. Pine published the work on EDFA, and EDFA amplified the weak signal for long-haul communication. So below this one is the block diagram for multi-core EDFA, where the input signal will combined with the palm source using a WDM, which is transmitted through a erbium-doped silica fiber, and the signal that we obtained at the end of the fiber will be the amplified one. Then this is the three-level system for the working mechanism of erbium-doped fiber amplifier, where on pumping, the erbium ion sitting over in the ground state will excite to the excited state 2. Here, the lifetime period is relatively short than excited state 1, so the ions will immediately decay back with no photon emissions, and the electrons, the ions will sit over here because here the lifetime period is a bit higher in a millisecond than this excited state 2, and the transitions that taking place between excited state 1 and ground state, where the population inversions creates, will give an amplification at a wavelength of 1550 nanometer. So here comes the motivations of my work. So the main motivation is to design the high speed, high bandwidth, low crosstalk multi-core EDFA, because the transmission capacity has reached the limit of single mode fiber up to 100 terabit per second according to the research. So in order to overcome that limit, space division has been proposed as a high capacity optical transmission technology. And along with space division, EDFA is used to amplify the signal. And from application point of view, industries and researchers have also foreseen this requirement of multi-core EDFA as a solution for of bandwidth expansions and high bitrate transmissions in an optical area network. So to design, our main motivation is to design and model a high performance multi-core EDFA based on space division multiplexing in order to reach the demand of increasing the bandwidth, speed of the fiber, and because of the increase of the internet traffic. Background study. So from the background study, I've seen that different researchers have used different transmission scheme for increasing the speed and the capacity of the fiber that is based on space division multiplexing. Some are like uncoupled multi-core, coupled multi-core, multi-core single mode, few mode fiber, Erbium-Doped few mode, Erbium-Doped multi-core single mode, multi-core few mode fiber. These are some of the literature survey based on multi-core optical fiber. So here we have seen that different author have used different arrangement of core to study the performance using different numbers of core. The arrangement like hexagonal, circular, square, rectangular has been taken by the researchers, and the parameters used to design these multi-core fibers are like core pitch, core diameter, cladding diameter, length of the fiber. And the major parameters are like capacity, crosstalk, losses are the parameters. Then these are some of the literature survey based on multi-core few mode and multi-mode optical fiber. So here also different researchers have considered different number of cores and modes to study the performance, and the parameters used to design are like cladding diameter, core diameter, length of the fiber, similar to the multi-core fiber literature we have seen in the previous slide, and different modulation format they have used to analyze the performance of this multi-core few mode multi-mode fiber. Then come the literature survey on multi-core single mode multi-mode fiber, Erbium-Doped fiber amplifier. So there are different researchers have taken different arrangement. The mostly used arrangement in Erbium-Doped fiber amplifier is the hexagonal and the circular one, and the number of core mostly used is of 7 core. And the parameters that are used to design this multi-core EDFA are the core cladding radius, pitch, length of the fiber, erbium concentrations, and the major parameters from these designed fibers are the gain, noise figure, and in few of the research paper, the crosstalk is attempt by the researcher. So from this literature review, we have seen that in multi-core fiber, ample studies has been done based on the core arrangement, using different core arrangement, and but here in EDFA, multi-core EDFA, variations in core arrangement has not yet been explored much. It has been limited to hexagonal and circular. So in my work, the problem that we have formulated, in our work, the problem we have formulated, we have studied the effect of core layout, then the effect of radius of the core on the performance of the EDFA in terms of performance analysis, in terms of gain and noise figure, mode analysis, crosstalk measurement with regard to the size of the core. Also, we have optimized the core with the parameters like pitch between the core, arrangement of the core, and size of the core. We have optimized this parameter, and after doing the optimization, we designed the parameter in order to design the multi-core EDFA with the optimized parameters to analyze the performance in terms of gain, noise figure, mode analysis, and crosstalk measurement. So these are the objectives and methodologies. In our thesis, it consists of 4 objectives. The first objective, that is to apply suitable modeling technique to model C-band multi-core EDFA. So there are different models used by the researchers. Some of the models like Giles model, Salage options model, average inversion model. The model that we have used is the Giles model because it provides a full spectral solutions that solve the steady state equations as assuming the gain parameters and the cross sections absorptions parameter. Then the second objective is to develop mathematical modeling of mode of light that is traveling through multi-core fiber. And to do this second objective, there are also different methods. The one that like beam propagation method, finite element method, transfer matrix method, the one we have used is the finite element method to solve the model of the mode of light traveling through the core. Then the third objective, after doing the modeling, we optimize the parameters to optimize different fiber parameters. So with a 2D analysis in COMSOL multiphysics, we designed a multi-core EDFA, and the parameters optimized are the size of the core, number of core, then pitch, then core arrangement. Then after optimizing, the fourth objective is to evaluate and optimize the performance of multi-core EDFA for high gain and low noise figure. So after doing the mathematical modeling and the optimization, we evaluate the performance of the designed multi-core EDFA in terms of gain, noise figure, mode analysis, and crosstalk. So these are the mathematical modeling. So these are the steps to do the first two objectives. That is the mathematical modeling to model C-band multi-core EDFA and the mathematical model to move for modes traveling through multi-core EDFA. So the first objective, that is to model, first a rate equation based on three-level system is considered, used, and for that, it is a steady state equation where dNi by dt will consider as 0. From here, the total density will be equal to n1 plus n2, where nt is the erbium concentration, which is remain constant throughout the analysis. And the intensity change will change with respect to the population density, emissions, and the absorption cross section. From where the field propagation equation in terms of the field power is expressed, and that field propagation equations will be integrated over a length 0 to z, from where we will calculate the gain. And in the second objective, that is the mathematical modeling for modes traveling through core, here the model solves the electromagnetic field using Maxwell's equations, where by considering psi common for both electric and the magnetic field, the wave equation for cylindrical coordinate is generated. Then here the fiber is of cylindrical structure, so the refractive index varies for directions, radial and the phi directions. Then using the Bessel functions, Bessel functions and modified Bessel functions are formed, from where we generate the normalized frequency. And then we generate a transcendental equations in terms of normalized parameter, and the COMSOL will do the above step has been done numerically using a COMSOL multiphysics tools, and at the end we observe the mode pattern in each core. The discussed steps in the previous are here. The mathematical expression of the discussed steps is given. These are the two atomic rate equations. So this one is a three-level system used for the amplifier model, where the transition from 1 to 3 is directly proportional to the product of pump flux and the cross-section, pump cross-section, and the transition from 1 to 2 is directly proportional to the product of signal flux and signal cross-section. And these two are the atomic rate equations, from where the total equation, because considering steady state equation, this dn1 dt, dn2 dt is equal to 0, from where the total population density will be equal to this, where this nt is the erbium concentration, and the population density equation n2n is expressed in this form, the equation 3, from where the intensity for signal and pump is equal to the power into the overlap factor divided by a core, where this capital tau s is expressed using this formula in equation 5, where RC naught is nothing but the radius of the core, which is known to us. Then omega naught square will be calculated using the formula, this one, where V is the normalized frequency. So as far as signal flux is concerned, so d phi as dz is expressed in this form, where in power form, this is the expressions which is integrated over a length 0 to L to calculate the gain. So these are the mathematical analysis for modes traveling through 7-core EDFA. So these are the mathematical expressions that COMSOL multiphysics will solve in using finite element method. So to solve this, the electromagnetic field using Maxwell's equations. And these are the basic the wave equations for optical fiber, where the electric field will vary in the radial directions and phi directions, where E I omega t minus beta z, where beta is the propagation constant and z is the longitudinal directions. And substituting into this equation into this Maxwell equations, we obtain the 6 Maxwell equations, out of which you cannot find Ez or Hz is equal to 0. Both are non-zero, because of which this is called an hybrid mode. And also here the fiber used in telecommunication has a very small index, like approximately 0.003, because of which both the polarization get coupled, and because of which the fibers are called linearly polarized mode. Both electric polarization and magnetic polarizations are present or get coupled. These are the cylindrical coordinates system equations, from where the normalized frequency is this one. And from this, after solving these steps, we generate a transcendental equations in terms of normalized parameters, from where we'll calculate the number of modes. And the modes are in the form of LPLM, where the number of phi directions is given by twice L, and the number of zeros in m direction is given by m-1. Then come to the contributory chapter work. This one is the first contributory chapter, a parametric study of 7-core hexagonal structured multi-core EDFA, which is published in the Journal of Optical Fiber Technology, Elsevier publisher. Here we have considered a 7-core hexagonal structured multi-core EDFA. So this one is the schematic diagram of 7-core hexagonal shape. The shape is of hexagonal. And to design this fiber, the parameters used are the cladding size 125 micrometer, pitch 28 micrometer, and the length of the fiber 50 meter. Here we have varied the core size. We have considered 5 different core size, because in this we will see the effect of core radius in the performance of 7-core multi-core EDFA. So we have varied the core size in order to see the effect. So the core size are 6, 8, 10, 12, 14 in a step size of 2 micrometer only. And the outcomes we have observed the effect of core radius in terms of gain and noise figure analysis and mode analysis. And after doing the study, we found a better geometrical configuration. For that better geometrical configurations, we have measured the crosstalk. These are the graph for gain and noise figure analysis for 7-core hexagonal structured multi-core EDFA. This one is for 6-core, 8-core, 10-core, 12-core, and 14 micrometer size of the core. Here, the graph 6, 8, and 10 is following the trends of increasing, then constant, and decreasing trend, which is followed by the existing literature survey. And also in all the cases, we have seen that at around 1550 to 1555 nanometer, we are getting a maximum gain. And as the wavelength increases from 1550 to 1560 nanometer, 60 to 65 nanometer, the gain starts reducing, which is due to the insufficient population inversions evolving out of the pump depletions, excessive pump depletions. And also, we have seen that the wavelength lower than the 1550 to 1550 nanometer, we are getting a low gain, because of which the modes, the lights traveling in that range of wavelength, the lights traveling to the core is very less in compared to the range of 1550 to 1555, which you'll see in the mode analysis result, we'll get to know. Then also, once the core size increase beyond 10 micrometer, that is at 12 and 14 micrometer, you can see the deformed gain graph, because once the gain core size increases, it will start moving towards the cladding regions, and because of which the core, and also the core, because of the increase of the size, the core gets overlapped and it moves to the cladding region, because of which some of the light traveling in the cladding regions, because of which we are getting a gain graph in this pattern. And from the comparisons of all the 5 radius, we have seen that with the increase of the size of the core, the gain starts reducing, and for and the gain from 6 to 10 micrometer, the difference of the gain is very less, that is 0.74% to 57%, which can be neglected. And once the size increases beyond 10 micrometer, the gain starts decreasing with a maximum difference. This happened because these are the console generated mode analysis result for 7-core hexagonal structured multi-core EDFA. So here we can see that at 6 and 8 micrometer, the lights are moving into the cladding regions and forming an evanescent waveform in 6 wave, because of which we are getting a lower minimum gain. And in 10 micrometer, you can see that through all the core, maximum intensity of lights are traveling through the core without any dispersions and loss. And once the core size increased to 12 and 14 micrometer, you can see that overlapping starts occurring in all the cores, because of which the gain in the 12 and 14 micrometer, the gain graph is of in a deformed manner. So from this analysis, we can see that at 10 micrometer, better result is giving without any evanescent waveform and without any overlapping. And from gain analysis result also, we can consider that at 10 micrometer we are getting a maximum gain. So we can find out from this observation, we find out that 10 micrometer is the suitable geometrical configurations in terms of mode analysis and gain analysis. So these are the model intensity graph for 10 micrometer radius of the core at 1550 nanometer, because at that range we are getting a maximum model mode pattern and maximum gain. So, and for each core we have find out the model intensity, and at core 1 we are getting a maximum intensity of model intensity. We're getting a maximum model intensity. Then the crosstalk. So the crosstalk is calculated for 10 micrometer radius of the core at 1550 nanometer, because that we have considered the best suitable geometrical configurations. And the formula used is 10 log 10 to calculate ICXT is 10 log 10 P core A to P core B by P core A, where core A, if we consider core A as core 1, then the power from core 1 to core 2, core 1 to core 3, core 1 to core 4, like that, core 1 to core 7 we have calculated, divided by core power through core 1. So similarly for core 2, if A is 2, then B will be from 1 to 7. Like that, we have calculated the crosstalk, and the total crosstalk is given in the below table, and the minimum crosstalk obtained for this one 10 micrometer radius of the graph is minus 45.5 dB. So with this, we have come to the summary of the first contributory work. So here we have designed a 7-core hexagonal structured Erbium-Doped fiber amplifier with reference to two important analyses. One is the gain and the mode analysis. And among the 5 geometrical configurations, 10 micrometers shows the best gain performance by obtaining highest gain, 42.09 dB, and maximum mode intensity going through all the cores. Then also here we have seen that the effect of core radius below 10 micrometer is found to be insignificant. Then the irrespective of the geometrical configuration, maximum gain for the entire geometric lies within within the range of 1550 to 1560 nanometer. So for the described multi-core EDFA, 10 micrometer core radius using a single wavelength of 1550 nanometer would like to suggest for designing purpose. So this was published here in this journal. Then the next contributory work, that is performance evaluations of two novel core structured multi-core Erbium-Doped fiber amplifier. So here the two novel structured are the T structured and the Y structured. The work is published in one of journal, Optoelectronics and Advanced Material Rapid Communications, Old City publisher, and the part of it is published as a chapter in lecture notes in Network and Systems, Springer publisher. So first we'll discuss the T structured multi-core EDFA. To design the T-structured multi-core EDFA, the parameters are like the core size is 10 micrometer, because we have considered 10 micrometer because in the previous contributory work, we have seen that at 10 micrometer, we are getting us better geometrical configuration. So we consider 10 micrometer, then the cladding sizes remain constant like in the previous, similar to the previous work. Here in this work, we are going to observe the effect of pitch on the performance of T-shaped. So we have varied the pitch, and also we have changed the core layout. So in this work, we are going to study the effect of pitch and the core layout in the performance in terms of gain analysis, mode analysis, and measurement of intercore crosstalk. These are the graph for T-shaped gain and noise figure results for T-shaped multi-core EDFA. For 25 micrometer, 28 micrometer, and 35 micrometer. And in all the cases, we can see that they are following the decreasing, then constant, then increasing, increasing, then constant and decreasing trend, which is similar to the hexagonal structured results we have discussed in the previous slide. And the maximum gain obtained here in all the cases is at a range of wavelength at around 1550 to 1555 nanometer. And once the wavelength decreases, the gain starts reducing. That indicates the saturations of gain amplifier. So here the maximum gain is obtained at 28 pitch 42 dB with a noise figure of 6.23 dB to 8.69 dB. And the difference among the pitch for the gain, the difference is 2.44% in both the cases. So these are the measurement of crosstalk for T-structure multi-core EDFA. The formula for 25, 28, and 35 micrometer pitch. The formula used for crosstalk is similar, is same as we discussed in the first chapter. That is ICXT is equal to 10 log 10 P core A to B by P core B A. So here we have observed here that once the pitch between the core increases, the crosstalk starts reducing, because when the pitch increases, there will be a maximum distance between the two core, because of which less overlapping or less coupling takes place, because of which we are getting a minimum crosstalks at higher pitch. And also beyond 35 micrometer we cannot increase, because even if the core size goes to the cladding regions, then again the dispersion starts occurring. The information will travel into the cladding regions. So here at 35 micrometer pitch, we are getting a minimum crosstalk of minus 50.70 dB. These are the mode analysis result of T-shaped multi-core EDFA. So from this analysis, we can see that at around 1550 to 1555 nanometer, through maximum intensity of lights are traveling, whereas wavelength lower than 1550 nanometer and higher than 1555 nanometer, less intensity of modes are traveling through the cores, and through some of the cores, very low intensity of lights are traveling, because of which we are getting a minimum crosstalk over minimum gain over this range of wavelength. Then come the effect of for Y structure, effect of pitch and gain, noise figure, and crosstalk performance for Y structure. To design the Y structure multi-core EDFA, the number of core is kept constant as 7. Then the size is same as T-shaped, 10 micrometer. Then the pitch we have varied, so we have studied the pitch effect in Y structure. Also in terms of gain, noise figure, measurement of crosstalk, and mode analysis. These are the graph for results for gain and noise figure analysis for 7-core Y structure multi-core EDFA, where the left y-axis is showing the gain and the right y-axis is showing the noise figure with respect to the operating wavelength. And in all the three cases, we are getting a maximum wavelength at around 50 to 55 nanometer, and the maximum gain for Y structure multi-core EDFA obtained at 28 micrometer is 42.25 dB, with a maximum with a difference among maximum gain is from 28 to 25 is 0.42%, and 22 to 35 is 1.31%. These are the results for crosstalk of Y structure multi-core EDFA. Here also, similar to the T structure, once the pitch between the core increases, the crosstalk starts reducing, because at 35 micrometer we are getting a minimum crosstalk of minus 52.98 dB. These are the COMSOL generated mode analysis for Y structured. In the Y structured, we can see that compared to T structure, we can see that in Y structure, through all the cores at this wavelength, all 1550 to 15, through all the cores, the modes are traveling, whereas in T structure, in few of the cores, the modes are not traveling, though through other core maximum intensity modes are traveling, but here through all the cores, modes are traveling, and because of which in Y structure compared to T structure we are getting a maximum gain. So with this we have come to the summary of the second contributory work. Here we have designed the two novel structure, that is T structure and Y structure, by varying the pitch difference, and the maximum gain obtained is 42 dB and 42.25 dB at the radius of core radius 10 micrometer at 28 pitch, which is closely followed by the rest of the two pitch. Also, an interesting observation obtained from the gain profile for the considered pitch is that the gain for T structure and Y structure is not significantly altered by the variations of the pitch. We have seen that the difference among the gain is very trivial. But however, the ICXT seems to be considerably affected. The lowest crosstalk is obtained in both the cases at 35 micrometer pitch at higher pitch, because there are less coupling taking place when the cores are wide apart from each other. Also, it's important to mention that judicious selections of geometrical parameters in the novel structure can deliver the gain that is equivalent to the mostly used structure, which is hexagonal structure, compared the result with the first contributory work, along with an efficient intercore crosstalk profile. So therefore, T structure and Y structure would like to propose designing with a core radius of 10 micrometer, pitch 35 micrometer using a C-band operating wavelength. Then the third contributory work, the effect of pitch on gain, noise figure, and crosstalk performance of different core structure of multi-core EDFA. Here, in this work, a comparative analysis is done. This work is published in the optic journal Elsevier publisher. So here we'll compare the performance for all the structure along with the hexagonal structure. The structured are T, Y, linear and circular. T and Y we have discussed in the second contributory work. Here we'll discuss the circular and linear, and the parameters used are the number of core sizes kept constant at 7, then the cladding and core size 10 and 25 micrometer. Then we have varied the core arrangement and the pitch difference. These are the results for circular shape gain and noise figure analysis, where the similar pattern can be seen as compared to similar as to the previous work T and Y and hexagonal, and the maximum gain here is also obtained around 1550 to 1555 nanometer range of wavelength, and as the wavelength increase, this gain starts decreasing. So the maximum gain at 28 micrometer is 41.96 dB with a noise figure of 6.01 dB to 8.45 dB is obtained, and the difference among the maximum gain is 1.79% and 2.36% for 25 and 35 micrometer from 28 micrometer. These are the crosstalk for 25, 28 and 35 micrometer pitch for circular set. Where the similar to T and Y structure, here also at maximum pitch, minimum crosstalk is obtained, that is minus 53.71 dB. And here, these are the mode analysis for circular set. Here we can see that at this wavelength, through all the cores, maximum intensity of light are traveling, whereas beyond this the wavelength lower than 1545 nanometer and higher than 1555 nanometer, we can see a low intensity or low intensity and dispersions can be seen from the COMSOL generated results. These are the graph for linear shape, where the similar to T, Y, and circular, maximum gain is obtained at around 1550 to 1555 nanometer of 41.58 dB with a noise figure of minus 5.16 to 7.94 dB, and the gain difference from 28 to 25 is 2.86 and 28 to 35 is 2.94 percentage, and the crosstalk for linear set is at maximum pitch, that is 35 micrometer, we are getting a minimum crosstalk that is minus 52.91 dB. In the mode analysis result of linear set also, we have seen that at this wavelength, we are getting a better high intensity of modes traveling through all the core, because of which at this range of wavelength, we are getting a maximum gain as compared to the rest of the wavelength. So here we did a comparative analysis of all the three work with a paper of K.S. Evedin, who is the pioneer of this field, multi-core EDFA. So this one is our first work, this one second and third work. We have compared with this paper as a reference paper. So the number of cores, then length of the fiber, lifetime, numerical aperture, we have kept similar to this paper. Then the hexagonal, they have considered a hexagonal structure. So in the first way, we have taken hexagonal structure, but here we have, they have considered a 3.2 micrometer radius. We have increased the radius of the size of the core, and we have seen the effect of the core size. They have considered only one core size. We have considered 5, and we have seen, because we have seen the effect of radius on the gain performance, and we found that at 10 micrometer we are getting a better results. Then these are the different shapes. In the second and the third work, we have varied the core layout, and other parameters are kept constant. So from 10 micrometer, so here we have considered 10 micrometer, 125 cladding radius we have kept since. Other parameters we have kept same for both, for all the work. And the one at Y structure, we are getting a maximum gain of 42.5 dB with a noise figure of 8.5 dB and a crosstalk of minus 52.98 dB. So Y structure is giving the better results. So with this, come to the summary of the third work, where we did the performance analysis for 4 different novel arrangement of the cores: circular, straight, T, and Y set. So from these important conclusions, we have drawn an important conclusion for the Y structure, that by analyzing the effect of pitch on both gain and ICXT, and with the variation of pitch, change in gain is minimum. We have seen the percentage in minimum is very minimum, very trivial difference, whereas the change in ICXT is maximum for the Y structure at a maximum pitch difference. So therefore, an efficient multi-core EDFA of Y structure can be designed, and by proficiently modulating the pitch. Also, so from the ICXT comparison for YT, circular structure, linear structured, with the hexagonal structure is also evaluated. Here, though the hexagonal structure is giving a bit higher, bit lower crosstalk than Y structure, that is minus 60 dB, because of its highly core packing density, but the difference, the pitch difference, the obtained crosstalk difference among the pitch is maximum in ICX for Y structure, because of which Y structure, then hexagonal structure, that is for Y structure 22.86, and for hexagonal 11% difference, because of which Y structure is considered as the suitable core layout structure. Lastly, the mode analysis for all the core structure along with hexagonal structure is studied, from where we have found that LP12 mode is dominating mode in all the cases. So with this, we have come to the conclusion of the overall thesis work. So here we have modeled the multi-core EDFA in order to describe the properties of the amplifier in terms of gains and noise property. Also, we did a mode analysis through all the through multi-core EDFA in order to analyze the mode patterns and its intensities. Then we evaluate the performance of the proposed multi-core EDFA in terms of gain, noise figure, mode analysis, and crosstalk. After optimizing the proposed design with parameters like radius of the core, we have considered 5 different radius, then optimize pitch, then arrangement of the core. So from this, we have seen that the core radius has considerable effect on the performance of multi-core EDFA. There exists an optimum value of core radius which demonstrate good performance in terms of both gain and crosstalk. Also, a significant observation is that the gain obtained is comparable for all the structured. We have seen that the gain difference is almost same for all the structures. So crosstalk is the property that decide the efficient multi-core EDFA structure. Limitations of the present work. So in every research work, there are some limitations. The limitations in our work are like the present work is limited to C-band wavelength. So further design the multi-core EDFA using L-band wavelength bears a significant potential. Then also further design of multi-core EDFA can focus on low mode dependent loss, then measurement of mode differential gain. And also in this work, present work, an inline amplifier has been considered to perform the analysis. Later pre-amplifier, booster amplifier can also be incorporated. Future scope of the thesis work. In present work, we have considered 7 core to evaluate the performance of multi-core EDFA. So in the future, the effect of variable number of cores on the performance of multi-core EDFA can be evaluated in terms of gain and noise figure analysis, mode analysis, and measurement of crosstalk. Then in this present work, homogeneous multi-core EDFA was designed. Homogeneous means within the cladding, all the core size are kept constant, whereas in the future there is an immense scope for evaluating the performance of multi-core EDFA by varying the core size of each core, that is the heterogeneous process. And beside heterogeneous process, coupled multi-core EDFA can also be explored in the future. Lastly, the whole work is of simulation-based analysis that can be experimentally examined by appropriate fabrication of the proposed multi-core EDFA, and the results can be compared with the simulated results to observe whether it's in line or what we can observe. Then these are the publications after the thesis work. So 3 journal. First is in Journal of Optical Fiber Technology, Elsevier publisher. Second one is at Optic Journal, Elsevier publisher. Third one is at Optoelectronics and Advanced Material Rapid Communications, Old City publisher. And one chapter in Lecture Note in Network and Systems, Springer publisher, and 4 conferences. So these are the references, and these 2 are the reference paper we have considered for comparison. So with this, I would like to acknowledge my supervisor, Dr. Subhash Arya sir, for his invaluable guidance throughout the research. He offered his mentorship for all-round development of my career. I would also like to offer my gratitude towards the head of the Department of EC, NEHU, for providing the infrastructure required and the necessary administrative support during the execution of the research work. I'd also like to thank my evaluation committee member for their valuable advice from time to time. Also like to thank the faculties and the staff of the Electronics and Communication Department, SOT NEHU, for their cooperation during the period of research. Lastly, I would like to thank my family members and friends for their constant support. Thank you.
Yeah, thank you so much, Balbindar, for presenting your final PhD defense Viva Voce on modeling and designing of space division multiplex based multi-core Erbium-Doped Fiber Amplifier. You have maintained good time. Now over to you, sir, Professor Srinivas.
Yeah, first let us see if anyone has questions. Then we'll look at the thesis. Anyone has questions, please? I think most of you know what she has been doing. So.
Participants, sir is giving an opportunity to interact with research scholar. Balvinder, you can show your PPT in fact, because yeah, on front page or something like that, you can put. So here among Himanshu or Madam Fida.
So 5 then. I will ask one small question.
Yes.
So you have not, you see in the multi-core, you do not consider the interaction between.
Sorry, sir. So I'm not getting.
The cladding thickness is very large. The distance between the cores is quite large, so there is no interaction.
Sir, it seems there was a voice break. We could not hear your voice seamless. So can you repeat your question again, sir? Sorry for it.
Yeah, in the multi-core, she did not consider the interaction between the different cores. The light propagation is independent in each core.
Yes, sir.
So the distance is quite large, I think, is it not, between the different cores?
So distance among all the cores, it's not too large, sir. A minimum distance like 28 micrometer pitch we have considered among the core.
Yes.
Then then in the second and the third work, we have reduced the size from 28. Then we have increased the size from 28.
Okay. Yeah, that is also quite large. Relatively, the mode field doesn't reach the other fiber core.
Okay, sir.
Yeah, I think that's correct, is it not? There is no
Yes,
interaction
sir.
between fiber cores with inside
Yes,
the.
sir.
Yes.
Yeah, crosstalk was less, means transfer of power
There
from
is no
one core to
crosstalk.
another core, and that was characterized using crosstalk parameter.
Yes. Crosstalk is not much.
Yeah, yeah.
Yes, sir. Crosstalk is not much. So reduce minimum crosstalk we have to build.
Yes.
Balvinder, can you show the answers of questions which sir has already
Let us
completed?
see what are the questions from the other examiners.
Pavan sir, are you here?
Sir, I am here. Okay.
Okay.
But actually, sir, frankly speaking, okay, I have missed some portion of it, okay, because of my some engagement, official engagement, okay. I was in front of computer only, but I was signing some documents actually, okay. I have missed, but anyway, okay, to Balbinder actually, first thing, okay, I wanted to congratulate her, okay, that nicely she have presented, okay, what I have listened, okay. One philosophical question I wanted to ask her actually, because
Yes.
this is the degree of philosophy. Okay,
Yes.
so uh, that means the day when you have been admitted over here and today actually, okay, what is the difference? Okay, you find in yourself actually
Okay, sir.
picking up this particular research work and now today. Okay, what is the difference? Okay, in you actually you are finding out.
So before, at the beginning, like in the year 2015, when I enrolled myself, at that time when I choose my topic, I came into this field, optical fiber communications. I have very less knowledge, and in this field, the basics like while carrying the work and how to do the literature survey and how to carry out the all the work through like research, administrative work, everything. In this whole 5 year, I have learned. So at this end, not much, but compared to 2015 and in 2021, I have learned very much in this field and how to carry out the research work. I have learned a lot from everyone and from my experience too, sir.
Okay. Now, any vital that means suggestion, okay, to your that means juniors, because many of your juniors I have seen, okay, they are also attending your presentation, okay.
Yes, sir.
So, any vital information do you wanted to provide to them?
Yes, sir. So first, I would like to suggest them. First, we have to do the literature very thoroughly, so that
Hmm.
we can formulate the problem of our research work in such a way that the at the end we get that results in a good way, for which we have to do the literature survey in a very extensive manner. So we have to do the literature. Then yeah, patience is one of the very important thing throughout the PhD phase. So one should have patience and do the work dedicatedly, and at the end, everyone will get the results, fruitful results.
Okay, okay, thank you. And another thing, actually, okay, just I wanted to, okay, last my year, okay, that actually, I understand, okay, being the head, actually, department is also having some responsibility towards the research scholar, okay, and in this particular regard, actually, your feedback is very, very important, okay.
Yes, sir.
So I just ask you to, okay, you please drop your feedback, okay,
Yes,
in
sir.
my mail, okay, in my
Yes.
mail, okay, do not hesitate.
Yes, sir.
Whatever is our shortcoming, okay, whatever the thing, okay, you have in your mind, okay, please freely, okay, you give your feedback, okay.
Yes, sir. Sure, sure.
Okay, that will help the department to grow actually, because in the field of research actually, okay, for the everyone, I'm just mentioning, okay, we have started our PhD program in the year 2013 only, and you can in fact say, okay, from 2014 only we have started the actual work, because the initial work was on the coursework only. So from 2014 to 21, this period, from the research point of view, it is not a very lengthy period. So your guidance will help us actually to grow. Actually, we are in a very initial stage. Okay, so that is from my side actually.
Yes.
Thank you, Arya sir, for giving me this opportunity for the interaction actually, and as well as external examiner also. Okay, thank you, sir. This is all from my side. Okay, being the head, and now you can proceed.
Thank you.
Yeah, let us look at the comments of the examiners. Other examiners, what did they say? Are there any questions from the other examiner? Did you make any modifications to the thesis
Yes,
after
sir.
the? Yeah, please briefly mention. You need not tell everything, but broadly, something. You need not worry about the spelling mistakes and corrections to the syntax, format, and such things. Any technically, if there is any important thing, you can mention.
So, sir, these are the comments I received from the examiner. So the first, in section 3.3.13, they've asked the multi-core fibers suppose several higher order fibers, higher order modes. What happen if all are single mode? And what is the reason for choosing multi-mode fiber? So here I put the answer. So in this proposed design, the single mode is not possible because of the core size is large and because of this V parameter is greater than 2.405. But if which supports multi-mode and few mode fiber, but if we convert this into a single mode fiber, we have to reduce the core size, and after reducing the core size, the spatial channel count will also decrease. Whereas in multi-mode, if we take an example of a multi-core multi-mode, we'll suppose 7 core and 9 mode, the spatial core channel count will be 63, whereas in single mode it will be 7 into 1 mode will be 7. So therefore the fiber capacity decrease in single mode by the number of times. So this is the answer for the first part. Then the second part, they have asked what is the reason for choosing multimode core. So according to in one of my paper, Y Sasaki in published in Optical Fiber Technology Journal, LCBA publisher, they've added that designed uncoupled few mode fiber address some of the issues that occurred in multi-core fiber and few mode fiber, that are like intercore crosstalk is one of the issue, then core layout, then differential model gain, then intermode crosstalks. And intercore crosstalk is the foremost issues in single mode core. So and that one we have addressed in our work, and that motivates me to do this research work in few mode multi-core EDFA. And the second question asked was that the results are quite, from figure 3.3 to 3.7, the results are quite close. Then what is the significance of different design? So I have mentioned the mentioned figure that is from 3.3 shows the effect of core radius in terms of gain analysis. And there we have changes the core radius in a step size of 2 micrometer, which is very less, because of which we are getting a similar quite results among the core. But from 10 micrometer, beyond 10 micrometer, we are getting the core the results in a different form in comparison to the 6 and 8 micrometer. We have seen from the variations can be seen from the figure from 3.3 to 3.7. Then the third comment is the reasons for similarity and difference in the performance among T and Y configuration may be mentioned in section 4.3.5, which I have added in this section 4.3.5 in page number 5 of the thesis. Then the fourth interpretation may be elaborated for variations. So for figure 4.4 and 4.5, an elaborate interpretation was asked, which I have added in section 4.3.5. Then the fifth question was asked, reasons for observation in chapter 5 may be given in the last sections, which the reasons I have added in the last section, page number 130, in the last section of chapter 5. And these are the references I given as a reference to answer these comments.
Professor Srinivas, sir? I think these were the questions which has been asked by sir only, and it has been. Of course, we go for multi-core as well as few mode, because in single mode, non-linear effects are there. If say hundred channels are sending through the single mode, and each carrying say some of course microwatt power, but they accumulate in very small core radius, then what will happen? Non-linear effects will be there, and hence this will reduce the data rate side. That is why we have to go towards fee mode also, with at the cost of little bit less data rate, but that data rate is again compensated by the multi cores. And other suggestions have been as, yes sir.
Yeah, that will depend on the power levels. The nonlinear
Yeah,
effects
yeah,
will depend on the power levels. When the signal is small, we can ignore the nonlinear effects.
yeah. But if WDM channels are there, sir, say 100 channels are transmitted, so even small power may be accumulated in the single mode fiber, and then non-linear
Yeah,
effects
yeah,
are
that's
visible.
right. In many of the WDM systems,
Yeah.
we try to reduce or the minimum power um, unless there is some other reason.
Yes.
See, it's not a long distance communication sort of problem, is it not? This is a small device. We'll see in this particular type of applications with multi-core,
Yeah.
we will try to we'll try to make a compensating device or something like that.
Yes,
Yes.
sir. Yes, sir.
That's the reason the distance is small.
Yes, sir. Yes, sir. Distance is small. So this will be applied like in the data centers where thousands of links are there. Then in some industries and all, where they have to connect the computers within a short distance. For that, this few mode multi-mode will be applicable, sir.
Yeah, anyway, from an academic point of view, it's an interesting problem, and someone has to take it to implement and experiment and all that. Maybe your department itself can set up facilities to work on such problems.
Yes,
Yes,
sir.
sir. We will definitely look into further explore and further extend this work.
Yes, and also if someone is interested, you can do on the chip silicon photonics on the chip. You can do multi-core. May not be like what she has done, but there are a lot of other ways in which you can extend this. For example, there can be many waveguides on a small chip, and they can like whatever almost like whatever she has done. There can be a lot of study that can be done. Yes, anyway, I think let us congratulate Balbindar, and she has done a good work. And today's presentation is also very good.
Yeah, thank you so much
Thank
for
you, sir.
your kind appreciation. That really motivate her as well as to us also, and it is very fortunate. We are very fortunate that in department uh, you happen to be a external examiner. It's really very great for us, sir. And
Yeah, I hope she will continue to do good work. She can
yes,
once
sir.
again
Thank
refresh. Of course, based on the
yeah.
research work that you have done now, you can do once again a new survey and see what are the recent developments and take up new problems. And then, if of course, definitely, I know that you will have your own students guiding towards the research and projects and so on. So
Yes,
I
sir.
hope you will be able to do good work and continue. Okay.
Yes, sir.
Yes,
Thank you,
indeed,
sir.
All the best.
indeed, sir. And yeah, I would like to also congratulate Balwinder for qualifying this uh, final PhD defense, and she happened to be prestigious Rajiv Gandhi Doctor Fellowship for 5 years because of her presentation, good writing skills. She has extensively done this literature survey. I was very impressed. Further, she has contributed as well. So pre-SCI index publication is good as far as my satisfaction is there. In a limited resources and being in northeast part of the country. So, so with this, if anyone has query for that, we would like to, uh, we shall appreciate. In fact, Professor Aljit Singh sir, uh, you must be very
बोलिए सर.
busy. Yeah, sir, would you like to interact or?
No, sir, nothing yet, sir. No problem, sir.
Okay, sir.
Thank you.
Thank you. Thank you so much for being here, sir. For your all support, head of the department, and all faculty members as well as member from Lightwave Communication System Laboratory, which they used to take part in our brainstorming reading session also. And again, thank you, our external examiner, Professor P. Srinivasan sir. In fact, I would like, okay, I think now I can stop this uh, recording. Then we can have that.